Okay, this session is being recorded. It's Tuesday, November the 10th. It's just after 9 o'clock in the morning. And today we're going to cover Module 6, covering network address translation, and Module 7, concerning wide area networks. And then you guys will be on your own for Module 8 VPN on the online book section on netacad.com, and there's 2 videos in there that cover portions of that module. There was a typographical error. Thank you, Poria. Thank you, Mr. Olivari, for catching that. In that next week's lab, in the syllabus said 10.8.3, but it's 10.8.2. That'll be a lab on network time protocol that we'll cover that on Tuesday next week. So today, this week on Thursday, when we come back, the people that come back in person in the lab, we're doing lab 6.8.2 on campus for the in-person lab, and that'll be covering network address translation theory and operation. Now, before I start on the F by PowerPoint, let me unshare this. I wanted to look at one of these announcements here, call your attention to something I want to share. The tab, the announcement. Okay, at the very top of the announcement screen, this is when you first log on to TCC Blackboard and click our class here. This is what you see. There's a new improved document for the upcoming Thursday, which is the day after tomorrow. It's going to be the Cisco Career Bridge online virtual seminar. And now there's one document here at the very top of the screen. When you click on this document, register for Cisco Career Seminar, it opens a PDF document. And if you roll down to the first link, halfway in the middle of the second page, that's the link you can click to go to the seminar, which will start at 2 o'clock our time, Central Standard Time. We're back on now, on Thursday, November the 2nd. And if you roll to the very bottom of the document, there is a Cisco Talent Bridge Career Prep course. That's a little mini course that's present on Cisco Networking Academy. And if you like to, you can enroll on that and give you a little background information. You might be a little bit better prepared to take that course. Okay, just wanted to point out that announcement to you. The Dallas-Fort Worth market for CCNA type people is hot. People that are getting their CCNA certs are getting hired right away. So if you want to check out that situation, please attend that seminar. Now, let's see. Okay, I'm still talking. You can still hear me good. Hang on just a second while I do a little attendance checking here. Okay, so I'm going to start with the first PowerPoint presentation. So hang loose here while I roll it up here. This presentation is, oops, wrong one, sorry. Share files, share this file. And there we go. Okay, you should be seeing a slide that says IP addressing services. The 2 major IP addressing services, we looked in the last semester, we looked at something called DHCP, Dynamic Host Configuration Protocol. And this was a protocol that automatically assigned IP addresses to employees or students or on the local area network. Pretty much everybody uses these days. It's been around since about 1995. So you don't have to do static addressing of host machines anymore. We do in the lab because we normally don't have a DHCP server. We do it by ourselves just to get used to it. So in karate, you got to take your 10,000 vols. In Cisco networking, you got to do your 10,000 static IP configurations just so you can get used to it. And then you'll implement DHCP and you won't have to do this. That's what all home routers do. Also, the second thing that home routers also do is that they do network address translation to the outside world, because you only get one global unique IP address from the outside world, a address that's routable on the internet. So I have, most of you guys have told me that you have cable. I still get my service from the phone company. I had this slow DSL service for many years. I originally was a cable customer back in the mid-90s. I got cable modem service, but switched to the telephone company DSL, and that was only 5 megabits. And now they've improved my speed. That service kind of got deprecated, and now I'm getting a super fast DSL technology that gives me about 75 megabit. So sorry, I can't compete with you guys that are connected to the cable company and you get 200, 300 megabits, something like that. Maybe one of these days I'll get the AT&T fiber and I'll blow you guys out of the water with 1 gig. So the purpose of network address translation is this outside globally unique IP address that you get, and I think mine's 199.99.99. something that I get from the phone company. You get one global unique IP address, but you don't want your inside network to be totally exposed to the outside world. So what network translation does is it allows us, network address translation allows us to use one IP address from the outside world, and then we can have as many inside devices as we need. Practical limit, maybe 4,000. And then those addresses, your inside address of your home router connected devices is most likely going to be 192.168. something. It's universally used for small networks that have 200 or fewer clients or so. And those will be translated to that outside address. And so your home router will do that on-the-fly translation between your inside address and outside addresses. And you'll have connectivity with the outside world and even add a little bit of security, because people in the outside world won't be able to pretend they're 192.168. something your neighbor inside your house and try to break into your system. So let's see how this works. So the public, what I call the globally unique public addresses, regional internet registries do this. There's different ones throughout the world. So in the United States, we have ARN. I call these people the name and number authority, because they're going to allocate you an IP address to use. They also will take care of your domain name. Now, we used to be able to get individuals and companies would go and get banks of IP addresses, but this has sort of been turned over now to the internet service providers. So if you need an IP address to communicate on the internet with, and you're a single home user, you'll get one address. But what if you're someone like Tarrant County College? Well, we go to an internet service provider and we get a bank of several thousand addresses because we have 100,000 students. So you can generally get those addresses assigned to you from your internet service provider. The problem is when you move to a different internet service provider, you get a different address. And you definitely don't want to run around to all your machines on the inside of your internet, inside of your private corporate network, and have to reassign static addresses to them. So with this network address translation scheme, you never have to change your internal numbers. You'll just get translated to the new outside address. So we talked before about this RFC 1918 address scheme, in which a few addresses are reserved for private inside use of residences and commercial businesses. And the so-called Class A address was 10. All the addresses beginning with 10. This is what Tarrant County College uses for our inside wireline devices that are plugged into the real Ethernet network. And then the Class B range is from 172.16. This is the range that we use for all our Wi-Fi access devices that are present on all the TCC campuses. So if you don't have any good internet campus connectivity at home, we've published a map now. You can drive to any one of our campuses and go to a certain parking lot, and you'll have good fast internet connectivity there if you need a connection. Or you can just go to McDonald's. And then the Class C range, that's a small Class C. What we used to call Class C was a small range of addresses, only good for about 250 addresses, typically used by all residences and smaller businesses. So what we're going to do is set up our company with one of these Class A, B, or C private inside addressing scheme. Like at home, you're going to be 192.168.1.1 or something like that. And then your home router will translate that to an outside address. We can't route private addresses over the internet. So that's one of the reasons we use network address translation, is to translate that inside private address into an allowable global unique address that can exist on the internet. Now, there's not enough public addresses to allow organizations to have one global unique IP address for every one of their host machines. It used to be the case back in the 90s when I worked for the college textbook publisher. Yeah, we were 167.208. something. I'll never be able to forget that number because I statically configured it 10,000 times. And all of the host machines on the inside of all our offices we didn't use NAT. We were globally connected to the internet. But there's much more people on the internet now. There's just not enough addresses to go around. And all the IP4 addresses have been used up. So this network address translation scheme allows us to translate our private 192.168.1.1 address inside your home to that public address that you get from your internet service provider. So in my case, it's the 199.99.99, whatever it is that I use. So NAT is a good solution for this. Let me say at this point that one of the big advantages of IP version 6 is there's so many trillions and trillions of possible addresses is that we don't need NAT anymore. But the migration from IP version 4, 32-bit IP addresses, to IP version 6, 128-bit IP version 6 addresses is going fairly slowly, so there's still a need for NAT. Okay, so the DHCP server inside the company or inside your residence will assign IP version 4 dynamic addresses to devices inside your network. Your NAT-enabled router, which is going to be your home router, or in your business it'll be a Cisco router or some other brand of router somewhere in that business, that will have internet global unique IP addresses that has been assigned to you, to your company, by your internet service provider, whatever your service provider is. So whenever you send a packet outside of your network, the 192.168.1.1 type address will be translated into that 199.99.99 address that's allowed to exist on the public internet. You can't send private IP addresses into the internet because remember we talked about access control lists. There was a chart. That's a means that the bad guys might try to hack into your network. So all public inside IP addresses, 10.172.16, 192.168, not allowed to exist on the public internet. They get dropped. An access control list will drop them. So a NAT device would operate, he talks about being a border of a stub network. A stub network is a network that has one single connection to its neighboring network. So in the case of your home network, you're a stub network. You're a residential stub network. In the case of Tarrant County College South Campus, we're a corporate stub network that links back to our home office, which is at the Trinity River campus, and then the home office at Trinity River has a connection to our internet service provider, who is CenturyLink. So a single connection to the network, we're going to do some type of address translation before we go to the public internet. So in our small business environment or our home environment, we're going to have an inside private network with the 192.168 or 172.16 or 10 dot networks like we have here at our fairly large Tarrant County College is one of the 20 largest colleges and universities in the United States. We're kind of big, so we're not really small business. So when a host on the inside network wants to access a host on the outside network, the home router at your house will take that packet and do a little rocket surgery and substitute that inside private address with the outside public address that you got from your internet service provider. So this is a translation table that will be present on your home router. It'll depend on what type of translation is being implemented. We're going to look at something called Static NAT, and then Dynamic NAT, and then port address translation, and see what these are typically used for. We're going to use Static NAT for our servers so that they can have the same exact address when people come in from the outside world. People want to get to our company's web server or a mail server or buy products from us. We're going to use Dynamic NAT for all our employee workstations because they don't care exactly what address they get, just as long as it has connectivity. And then port address translation is a feature that, for example, at home, you've only got one global unique IP address, probably. You can pay $200 a month and get 4 or 5, but most home users don't need that. If you're a business, you might need that. Port address translation will share one global unique external IP address with maybe dozens of internal addresses. So let's look at this terminology. The inside network is usually an organization's local area network. It could be your home network. Let me see, turn on the pencil. So this is area over here. Some local area network with several devices. The outside network is going to usually be the internet. The jagged lightning bolt thing here is the way we normally designate you're connecting to an internet service provider, or you're connecting through a leased link to the home office. So that's the outside-based network. So a local address is how a node on the network is seen by another node on the same network. So at Tarrant County College, when you come into the laboratory classroom, and your workstation is 10 10.144.100.1, and you can see the other workstation, and your other lab person that's in the next row from you, he might be 10.144.100.2, and you can ping them directly. You see them by those local addresses. So in the outside world of the public internet, we can have public IP addresses. So these two servers have similar addresses, and they can ping each other, and they see each other with their addresses, non-translated type addresses. Now, the global address is how a node on the network is seen by the node on the other network. So in the case of the big eyeball here, who is maybe at the web server farm at the data center that's at Cisco, he doesn't see your address. When you log into the workstation in the classroom and you're 10.144.100.1, he does not see you as that number. Your address has been translated because 10 numbers are not allowed to exist on the public internet. They are dropped. So in the router that connects you to the internet, he will do that network address translation function and change your address into that global public address that will exist on the public internet. And then you'll be able to communicate with them. Now, how do you see addresses on the outside world? You will see them by their globally unique IP address and that server farm for that particular organization. So an inside local address is almost always an RFC 1918 address. 10 dot something, 172.16 dot something, 192.168 dot something. The inside global address is that address that you got from your internet service provider. It's going to be a valid global unique public IP address that's allowed to exist on the internet, not the 192.168 that you're at home. That's your inside local address. So the inside global address is how you appear to the rest of the world. So if you have a cable modem and you have 12 devices at home, you appear to the outside people on the internet as one very, very busy host with 12 things going on at the same time. So the outside global address is the address that the internet host has, that you can, when you do that DNS, when you type in, go into your web browser and go to netacad.com, the DNS service looks up the actual global unique IP address for netacad.com, and that's the outside global address that you see. And outside local addresses beyond the scope of CCNA, don't worry about this. So NAT works in this fashion. You're going to send a packet from your PC, and you're going to have a source address of 192.168. something, not allowed to exist on the global internet. So that's going to go through to a border gateway router for maybe this is a small business and it has a couple of routers. And that border gateway router is going to translate that inside address, 192.168.1.10. That needs to be translated into an outside address so that it can exist on the internet. So your source address, which used to be 192.168.10.10, then that would be dropped if it was on the internet, has been translated to 209.165.200.226. So the little rocket surgery has taken place on that packet. And inside the router, your home router maybe, or corporate router, he makes up a little table and keeps that information in there so that when the answer comes back from the web server to you, he knows to correspond to that local packet and translate it back to that local value so your PC can receive it. So this is the sending function. The receiving function, when the answer comes back from the server, hang loose 1 second. So when that answer comes back from the server through the ISP and hits your home router's got to do reverse rocket surgery. He's got to take out that global address that was temporarily assigned to your packet and replace it with the inside global address. He goes back to this table here and says, oh yeah, that's the answer to the original query that he sent. Put the original address back in there so the destination address is now corresponds to your machine, your workstation, and you'll get that web page that you asked for back on it. Now, this sounds very complicated, and it sounds like it would take a very long, long time, but it does it in the twinkling of an eye, very, very fast, and it's really doesn't slow the communication down any, because remember, routers have to encapsulate and de-encapsulate packets anyway. It's very easy for them to simply do a little black magic on that destination address and source address and make this network address translation function work. Okay, now let's look first of all at dynamic mapping. Normally, if we were at home, we're going to get one outside global address. But if you're a business, you might need several of them. So let's say that I had got a bank of, how many addresses is this here? 81 to 86. Let's see, I only went to public school, but that's 6 addresses. So for example, AT&T offers a DSL service for businesses where you get a bank of 6 static addresses that you can lease from them. But you have 8 employees. So if I have only 6 addresses to the outside world, and I have 8 employees, after employees 1 through 6 get on the internet, and 7 and 8, they didn't show up to work till late, they have no sessions because they're locked out. We'll have a workaround for this. We'll fix this later on. But this is just illustrating a problem with dynamic mapping. So static mapping is important so that maybe I bought those 6 addresses from the outside world. And 10.1 is my web server. And 10.2 is my mail server. And I want those devices to always have that exact same address that the outside world sees so that I can map them to DNS. And when you type in mywonderfulcompany.com, you'll always get this 81 address and go to my public web server. Send me an email, will always be 179.net82, and you can go to my mail server. And the other 4 addresses, I'll use the technique we'll see about later. We'll do some NAT overloading and make all my inside devices, client and workstation machines, be able to use this. So if I do this static addressing, though, without using the technique we're going to see in a minute, I'm limited again to 6 addresses. I've statically mapped them on a one-to-one basis to them. Now, if I only have 6 employees or 6 computers, this would work just fine. But if you have more than that, we're going to use another technique later to sort of cheat and use more. So port address translation allows us to use a single public IP address, or maybe a bank of 6, or maybe a bank of 1,000, like Tarrant County College uses, and assign it to, well, let's see, 65,000 inside hosts. Where does that come from? How many bits is in a port number? A port number is a 16-bit value. So 2 to the power 16 is 65,536 possible values. Well, maybe 4,000 is more realistic for this. So what we're going to do is do the same thing that a single computer would do. A single computer running TCP and UDP would have unique port numbers for each web page you got on there, and they wouldn't mix up the data. This just allows us to expand this to more than one PC. We can have several PCs inside, and then using unique port numbers, we can keep the traffic separate, and each person gets his traffic and doesn't get the other person's traffic. So with port address translation, we're going to track and translate the source IP address and the destination IP address, and now we're going to start tampering with port numbers too. This is going to be enough to uniquely identify each individual of these 4,000 connections, or probably just the 10 or 12 you have at home. So with port address translation, or NAT overload, what we're going to do is we're going to have some host machines here, and they each have a session to 2 different web servers that are present on the internet, 2 different companies maybe. So we're going to take this inside address, this 192.168.10.10, and this 192.168.10.11. We're going to translate those into an outside source address. So this guy became this address. This guy became this address. And then they get translated into the outside world. Then notice they both have the same exact IP address. How do we tell them apart when we come back? They have unique port numbers. So the port numbers allow us to differentiate these 2 different machines from each other. So, 65,000 possible different values here, so we can easily do this. Then when the information is transmitted to the outside world, he'll think I have this address, not this address. And when he sends it back to me, the table, the network address translation table on the router will flip-flop them back again, do the reverse rocket surgery, and when they come back, it'll be translated back. So the NAT table, outlined here in red at the bottom, they've translated that inside local IP address to the global IP address, and it's a valid address that's allowed to exist on the internet, and it's transmitted back and forth. So port address translation, we'll maybe use the next available port. So In this case, both workstations just coincidentally have used the dynamic or ephemeral port number 1444, and they're both supposed to go to the outside world. Well, he can't give them both that port number, so he's going to give machine 1 may get 1444, the global address, and the second machine would get maybe 1445, so that they're separate from each other and they can be told apart from each other. So here's some benefits of this. This conserves the legally registered addressing scheme. It's more flexible, and it gives us consistency if we change ISPs. We don't have to renumber all our inside host machines. You don't want to do that, I can tell you that. And it gives us some security, because when you do that TCP three-way handshake, sync, ACK, and you establish a connection with an outside server, and he sends you the information back, if it doesn't match the numbers in the NAT translation table, it'll discard it as bogus. So it's rather difficult for people to break into your internal network through a network address translation router and try to, hack your network. Okay, there's a downside. Performance is slightly reduced because he's got to do all this rocket surgery about replacing numbers with other numbers. End-to-end functionality may be degraded. Now, it turns out that the killer applications of the internet are mail, email, and web, and that works okay. End-to-end traceability, for example, ping, could be lost. If you're doing some tunneling, like VPN tunneling, we'll see that next week, it could become more complicated. It could possibly disrupt some TCP connections. But in general, it works very well. Everybody uses it, and we're going to continue to use it as long as we have IP version 4 in our networks. And gradually we'll migrate to IP version 6 where we don't have to use it. So let's look at the configuration for this. First of all, we're going to have to decide which is an inside address and which is an outside address. Obviously, oops, click pencil. There we go. This is our inside network. Obviously, we can see this. The router doesn't know. He has to be told. So we're going to go and tell that router that this is the inside port and this is the outside port. So he knows what's public facing and what's the trusted internal network. So the first step is we're going to type a line of code that says IP NAT inside source static, and this is an example of static RAM. We're going to take this server, inside local server here, and that's our web server. We want to be able to statically map that to one single globally unique IP address on the outside world. So we want that inside private address of 10.1.1.2 to always be what's in our DNS record for our company. 179.23.2.2 is the address that resolves when you type company.com, and that way they can see our web server. So I'll type IP NAT inside source static 10.1.1.2, 179.23.2.2, and that establishes that. Now we're not done yet. We need to tell, you remember when we created the access control list and then we had to apply it to an interface port? Same thing with NAT. We created the NAT translation, the NAT mapping. Now we got to tell the router which port is the inside private trusted network and which port is the outside globally unique network that we need to translate the addresses to. So in this case, he's gone to the Ethernet port, which is our inside port, default gateway for inside client machines. Of course, we have to say interface, fast Ethernet, gigabit Ethernet, and then we have to give it an IP address. But then we're going to say IP NAT inside. This says that identifies the NAT function. This is the inside network that you're going to translate addresses to go to the global public internet from. Then we're going to go to our outside port. In years past, this was likely a serial port. These days, it's more likely to be an Ethernet-based port. We're going to say interface number, assign the IP address that we use to get to our service provider, and then say IP NAT outside, and that will mark that port as an outside port, and he will translate back and forth between those according to the NAT table that we made in the last slide. So here, 10.1.1.2 will always translate, because it's static mapping, to the outside public address of 179.23.2.2. That's where all our customers expect to find our web server so they can order our products. So let's talk about Dynamic NAT now. And that was Static NAT we did in the back. Where every company, every commercial company is going to have a few static NAT addresses for their servers. For example, we have a static NAT assignment for the Web Advisor server. We have a static assignment for my TCC Blackboard. We have a static NAT assignment for the tccd.edu public website. But we're going to use Dynamic NAT for everything else. All our employees and student machines, and they just need internet connectivity. They don't care what their number is. So here's the way Dynamic NAT works. We're going to create a pool of addresses, of outside addresses, to be used for translation. In that earlier slide, we had 6 or 8 addresses, 6 addresses and 8 clients, and only the first 6 could get helped. Then we're going to use, remember access control lists? We're going to define an access control list to specify which inside addresses get translated to the outside world. So maybe the administration department gets translated, but the line workers on the production line don't get it. Or perhaps in a public school environment. The kindergarten through 6th graders till they're about age 13, they don't get outside access. The older kids that are over 13, yeah, they get some kind of access to the internet. Then we're going to specify the dynamic translation, which is the inside addresses that are being allowed by the access list. This will go to the pool of outside addresses we've set up. And those eligible inside people will be allowed to get an outside address and actually communicate with the internet. Then the next step is we have to mark the inside port and the outside port on our routers. Which outside port connects to the global internet, to our ISP? What inside port is the default gateway port for all these guys that are inside my company or school? So let's define a named address pool. Here's the syntax. IP NAT pool. Make up an arbitrary name. In Cisco configuration, it's considered good practice to, whenever you make up a name, like a DHCP pool name or a NAT pool name, do all capital letters. It makes it sort of pop out at you when you look at the show run command. Makes it easy to see. He will accept the upper or lowercase, but I recommend you use uppercase for this. And then we're going to specify our start IP and end IP that we were given by our internet service provider, along with the subnet mask. And this is one of those few commands where you don't have to type the 255.255.255.0 and you always make a typing error. This is one of those few commands where you're actually allowed to use /24, which is much easier to type. Yeah, why not those Cisco network engineers let us type /24 when we type our IP addresses? We have to type 255 all the time. So here's an actual example. We've created the IP NAT pool, and it's called it NAT pool, all capital letters. That's good practice. The range of addresses we got from our ISP, from 80 to 85. It looks like we have 6 static addresses that have been given to us by our internet service provider, and it's a /24 subnet mask. And that defines the pool of addresses to be translated. Now, we're not done yet. We have to define an access control list to define which addresses get translated. And we have to assign the inside and outside ports on our router. So let's make an access control list. It's just a standard access control list because we're just looking for source addresses. So this is going to be an access list that says access list, make up a number from 1 to 99, and permit which addresses are being allowed to be assigned to the outside world. Okay, how about this? Access list 1, standard. Permit anybody that's on the 10.1.0.0 network if, look here, the zeros means must match exactly. All ones, 255s means I don't care. So that means if your IP address is 10.1, must be 10.1, and the last 2 octets, I don't care. It can be 10.1.2.3, 10.1.255.255. It can be any. Those last 2 octets can be anything, and then we'll match this list. Just so long as the first 2 octets are 10.1, you match this list, you are permitted. Oh, the elementary school kids, they're on 10.2. They're not permitted. So that takes care of the access control list. Then we're going to specify dynamic translation between the inside addresses and outside addresses with this syntax here. Let me see, is he giving us a example? Here we go. IP NAT, inside source list. What's that one? Access control list number 1. The pool, NAT pool from step 1. Okay, now we define that that list is to be matched now according to the access control list and according to those 6 addresses that we were just given to our internet service provider. Oh yeah, we have to assign the inside and outside interfaces on the router. So we go to the inward facing router interface that goes to our internal people and say NAT inside. We go to our outside connection that goes to our ISP, and we give it NAT outside, and the configuration is complete. So all inside hosts are eligible for NAT. Only one problem. Only the first 6 hosts will get serviced. And the 7th host and all the ones beyond, they'll have to wait in line. They won't get a connection. So let's fix that problem and do what all the home routers do. So I could simply buy 4,000 IP addresses from the ISP, but that would be a big expense. I could allocate more than one address. But what I'm going to do instead is I'm going to use the overload keyword. And when I make that statement, port address translation statement, I'm going to add the keyword overload, and that means, oh, if you only have 6 global IP addresses, use port number black magic and allow more than 6 clients to be connected at the same time. Just like your home router has one global unique IP address from the cable company, and they give you as many connections as you need at home, your 1 or 2 dozen connections you need at home for all your devices and all your Rokus and all your Game Boys and Xboxes and all these other things that need IP addresses to the outside world. So we're going to do the step 1, assign the IP address received from the ISP as the IP address of the outside interface. We're going to do the same thing in step 2, make a standard access list. Who gets outside access? Probably everybody at home router. I'm going to do number 3, dynamic translation statement. Specify the access list. Even if you want everybody to get to the outside world, you still have to use an access list and just permit everybody. And then include the overload keyword, which here means start using port magic to allow more than the 6 people to be connected. And then lastly, make sure you specify the inside and outside interface ports on the router so he knows what's inside and what's outside. So here's an example here. Inside network, your home router maybe, your ISP like a cable company. So access list 1 is going to permit, at home you're probably 192.168. something. This access list will permit anybody who's 192.168. anything to be allowed. In the statement IP NAT inside source list 1, that access list is just made up. Interface S010, that's the outside port to the outside world. When you do the NAT translation to that, use the overload, PAT overload feature. And use port number so you can use more than 6 numbers. Then interface S00 on the inside world is established as our inside trusted network. And interface S010 to the outside world is established as our untrusted public global network. So maybe you get more than one address. Okay, in the previous example, we only got at home, you only got one global address. Maybe you did that. How many addresses is here? From 226 to 240. That's 14. That's a slash 28. We have 16 raw addresses, but we lose the 4 zeros as the network identity. We lose the 4 ones as the broadcast function. So we get 14 available addresses to the outside world. And then those 14 addresses can be overloaded and assigned to as many inside hosts as I may have, thousands maybe. Now, you can go to the router prompt and type show IP NAT translations and see all the translations that have taken place. So show IP NAT translations will show all the translations that have taken place. And then show IP NAT translations verbose will show us even more information about that, some detailed metrics and numbers. Show IP NAT statistics will show some general statistics about the translations that have taken place. And sometimes when you do a NAT lab, they may tell you to clear the previous translations out because you've changed the NAT configuration. You've done one kind of NAT, now you're doing another type of NAT. Now we could just copy, run, start, and reload the router, but that would take 3 minutes. So if you type clear IP NAT translation star, that will clear out the existing NAT translation table, and then you can try your new code that you set up to do this. It'll warn you like crazy. When you type clear IP NAT translation, it'll warn you, oh, that's going to wipe the table out. You really, really want to do this. Now, a word about debug. We have show IP NAT translations and clear IP NAT translation. Okay, debug function is present in Cisco routers and switches that allows us to sort of peek under the hood and all the CPU processes that are going on, it's kind of dangerous because it ruins all the speedy optimization techniques that they've done for the routers and the switches. Cisco Express forwarding and fast switching and things of that nature. When you turn on debug, you turn those off because you've got to look at each and every packet and see if it needs to be shown on the screen because of the debug command you typed. So good practice with debug is only turn debug on for a limited time to find out what you need to know to troubleshoot your problem, and then turn off debug when you're done. In this case, he's turned on debug IP NAT, and all the NAT translation functions that this router is going to do are going to show on the screen as they take place. If it's a lab router and there's not a bunch of traffic going through it, it's no big deal. But if it's a production router in a real business and you turn on any type of debug, it could cause packets to be dropped. So only turn on debug for a short amount of time, figure out what it needs to tell you, and then turn it off again real fast. Or otherwise people will really start dropping traffic. Okay, hang loose one. I'm going to stop showing this, and we're going to go on to the WAN functions. Now, a word about WAN before I get started into this stuff. Traditionally, WAN connections between branch offices and home offices were through serial ports like T1 lines and frame relay lines. And the typical branch office Cisco router always had 2 serial ports and 2 Ethernet ports, just like the ones that we have in the lab. These days, it's more popular to use what I call Ethernet handoff technologies. So instead of having to translate our Ethernet frames into serial point-to-point protocol frames through a serial port like a T1 line or a frame relay line, or ISDN line back to the home office, Tarrant County College gets their service from Ethernet handoff technologies like Metropolitan Ethernet or Carrier Ethernet. You get your service from the cable company. They give you a cable modem with an Ethernet plug on it. You don't have to plug in a serial plug and do the translation with the router. The telephone company with their DSL and super extra fast DSL services give you a DSL modem. It has an RJ45 Ethernet plug on it. So you don't have to do any serial conversion to Ethernet connection. So Cisco, about a year ago, when they revamped the CCNA curriculum, they pretty much took out a lot of the stuff having to do with serial ports. We're going to have some theory and operation in this chapter, like point-to-point protocol over serial ports. But these days, if you're not in a third world developing country where you're using old technology, you're probably going to use some Ethernet handoff technology that's a more modern technology. So we're going to look at the purposes of a wide area network and check out how they go here. Now, before I go to the next slide, let's just do the big 3. What's the big 3 of a local area network? Local area networks, very fast technology like gigabit Ethernet. 100% always on availability. Like the dial-up modems in the 90s where we'd have to get somebody off the line to dial up to the bulletin board system. And so very fast connectivity, always on, and the private connection. Now, wide area network connections are between your cable modem and the cable company. That's a WAN circuit. It goes back to the cable company facility. Or if I have a lease circuit between the South Campus and the Trinity River Campus, that's a lease circuit, the wide area network. So wide area networks they used to be slow, pick up dial-up modems. Now they're usually a dedicated connection that's always on. They used to be serial ports, now they're typically Ethernet ports. I can't dig a ditch along the highway and put my own fiber optic cable between the campuses. I'm not allowed to do that. The only people that can do that are the telephone company type people. They can lay their own fiber optic cables, and then we can just lease some capacity on their fiber optic cables. The old rule about WANs was they were slow, like a dial-up modem speed, 55 kilobit. T1 lines, 1.54 megabit. Now with the newer technologies, like we have 10 gigabit connectivity over fiber optic cable between our campuses. You can get 1 gigabit connectivity from the cable company or the phone company to connect you to the internet. So the rules are changing now. They used to be considered slow, now they're considered very fast. So the purpose of a wide area network, the purpose of a local area network was to connect within a small geographic area, like in this building, in this office building, on this South Campus. The LAN is owned and managed by the organization or owned by the residential user. There's no fee to use the LAN. You just buy the products and you put it in yourself. So very high bandwidth speeds using the wired Ethernet at maybe gigabit speeds, Wi-Fi services. Wide area networks, you don't get to dig the ditch yourself. You have to lease the service. You have to pay for it. You have to pay a monthly fee for it. They can give low bandwidth speeds or they can give high bandwidth speeds. And the trend these days is to be much higher rates of speeds, even over intercontinental distances, long distances. But they're not owned by you. They're owned by the phone company, or they're owned by the internet service provider, or they're owned by the cable provider, or they're owned by the satellite provider. So WANs are used to connect LANs. We use a WAN provider to connect our LANs at the South Campus and the Trinity River Campus together, where we can get connected to we have a bank, we have a data center at the Trinity River Campus that has all the servers for all the functions of the company. We used to have servers everywhere. We used to have a server in our business building for our own use. But that all got moved to the data center because it's all our eggs in one basket type of technology. So a private WAN is a connection for a single customer. Legacy, traditional example of this would be a private T1 line between the home office and the branch office. No one else is using that line. So we get guaranteed bandwidth because no one else is sharing our bandwidth. We get our security because no one else can tap on our data. We have a guaranteed service level. The phone companies will actually give you a guarantee that it will be available, like 99.999% of the time. A public WAN connection would be like, your internet connection. Service levels are usually not 99.999%, the 5 nines. So, and if you have a cable modem, a residential connection, a cable modem, or a telephone company connection, it's not guaranteed delivery. It's best effort only. It may go out for a few hours. And there's no security because you're sharing. This is wild west on the internet. Everybody can see all your packets. If you need privacy and security, look at that next chapter after this one and do a virtual private network. So here are some different topologies. Let's look at what these mean. These are physical topologies. A point-to-point topology. A point-to-point topology is like a private line between one place and another place. So I can get a connection like a multi-protocol label service MPLS type connection or a T1 connection or whatever I want to get between the two sites. Now, if I have a lot of locations, it can become very expensive because I have all these multiple point-to-point connections. The phone company will be very glad to lease them to us and be very glad to collect the recurring monthly charges we get every month for this. And it's typically a layer 2 service. I can stick my Ethernet frames over that site A and it'll go to site B. Hub and spoke topology. Now this is what we're going to use with the college. The hub is Trinity River Campus. That's our hub. That's our home office. The spokes are the South Campus and Northeast Campus and Southeast Campus. All our various campuses are connected together. So this way we can connect between the home office and all the other offices, and any South Campus can communicate with Northeast Campus. It has to go through the Trinity River home campus to get connected. Dual home topology is multiple connections. So at the Trinity River campus, we might have 2 connections. And if one of these devices fails, we still have another one that you'll be able to connect to. Now, this is more expensive, more complex to set up. But in some industries, we don't want any failures to occur. If there's any single physical failure of any kind, we don't want operations to stop. So think of a RAID drive array for a server. If any one drive fails, the data isn't lost. Or a UPS for a server that keeps it running if the commercial power fails. Or in networking, we're going to run multiple connections, and if that router on the bottom goes bad, we have another router that will still be working. So more expensive, that's job security for us network guys. In a fully meshed topology, we're going to have virtual circuits to go every which possible way. So if a backhoe digs up this fiber optic cable here, we still have an alternate way of getting connected back to that office. This is very fault tolerant. It's also the most expensive. So some companies may use partial mesh topology, and maybe the busiest locations are connected together, and the smaller location doesn't get multiple connections. So carrier connections is this concept that we're going to go to a service provider like the phone company or a cable company or some sort of service provider, and they're going to give us a service level agreement as to what they guarantee. Now, home and residential connections, you don't get an SLA. Best effort only. If you want a service level agreement, you're going to pay like $1,000 a month for that gigabit connection, not $80 a month. The service provider may not be the carrier, and they may be someone who resells that service. So, for example, you can get a DSL connection from the AT&T, or you can go to third-party providers that resell this service and get it from them. So a single carrier connection is when you only go to one provider. So I've only got a single connection to AT&T. Now, what if I got another connection to, besides my existing AT&T connection, maybe I got a connection to a cable company as well. And you can get routers that will connect to both of them and automatically load balance between them and use one if the other fails. But of course, it's more expensive. You have to pay 2 bills. Okay, hang loose. I'm going to go past the span nonsense, marketing nonsense. Let's see, we're on 13. Okay, wide area network standards, and here are the people that do this. The Telecommunication Industry Association and Electronic Industry Association are trade groups that represent the people that sell communication and computer equipment. It's to their advantage that all this stuff works with other equipment vendors, manufacturers equipment. It used to be the case many years ago that you had to buy all IBM disk drives and all IBM computers, and you couldn't buy somebody else's disk drive. But now they all work using TCP/IP, they all work with everybody else. The ISO is a standard that International Organization for Standardization that does things like, in the automobile industry, there's so many threads per inch of a screw, number 8 screw. All those have to be standardized so that everybody can manufacture stuff. The ISO are the same people that came up with the dreadful OSI 7-layer reference model, which we're sort of taking out of Cisco now. We're going to stick with the TCP/IP model. The IEEE is an institute of electrical and electronic engineer students and graduate students and professional engineers in the field. They came up with, for example, the 802.3 standard for Ethernet, and they made it more complicated than it really needed to be. So we're going to use the standard Ethernet 2 concept that the internet actually uses today. So if we look at the physical and data link layer, at the physical layer, at the layer 1 layer, we're going to have the actual, it's probably going to be these days flashes of light going through a fiber optic cable. It could be electrical currents flowing through a twisted pair Ethernet cable. And it's just bits. The bits don't care. The physical layer doesn't care what the upper layer information is. Any more than the telephone doesn't care what language you're speaking in. He just translates the sounds and sends it to the wire. Then at layer 2, at the data link layer, how are we going to make the frames that put these together? So they're going to be Ethernet frames, they're going to be point-to-point protocol frames. So when you go to a Cisco device and you type show interfaces and it says it's up and up with the other device, layer 1 means the physical wires are plugged in. We can transmit the currents representing the bits. The second up means we both agree as to what the protocols are. We're both speaking point-to-point protocol, for example, and we can communicate back and forth with the other ones. The telephone analogy would be if I use the telephone and use the telephone, if we both speak in Italian, we can both speak to each other. If I only speak Italian and you only speak Yiddish and we have a good phone line connection, we're not going to be able to speak to each other because we don't have a common language. That's like a layer 2 protocol. So here is some WAN. Let's see. Let's stop here and look in our backyard, and there's a little gray box tied to the back of your house that your phone company connection comes into. The telephone company is responsible for everything up to that gray box. The little wire comes down from the phone pole, and it attaches to the top of your house, and it's stapled down to this gray box, and then your inside home wiring attaches to that. And you're responsible for your all inside wiring in your phones, unless you want to purchase the agreement from the telephone company where they agreed to maintain your inside wiring. So if you open up that box, there's a little pigtail connection, looks like a little tiny 1-inch telephone cord. If you unplug that, you've isolated the telephone company responsibility wiring that goes up to the pole from your inside wiring. So if your phone stops working, go out to the box, open the door, unplug the pigtail, and plug in a no good working telephone into that little RJ11 connector. And if it works okay, that means the phone company is okay. It's not their fault. If you plug in a no good working telephone and it doesn't work, well, it is the telephone company's fault. So you have to call for service. So the telephone company is responsible for maintaining everything up to that. We'll call that a demarcation point. And they are called their telephone company, that's called the local loop, that length of wire that goes away from your gray box, goes up to the phone pole and vanishes out of sight. They maintain that wire. If a tree branch falls down and knocks that wire down, they're going to fix it. You don't have to fix it. That goes back to your local telephone company's central office, and you're connected through their connection they have to wide area network connection circuits to the real network that you can use. That's the service provider. You are the enterprise or the residential user. You purchase your own telephones, or you purchase your own modems, and you purchase your own equipment and you plug it in there. So this DCE, data terminal equipment, that's the end that connects to the WAN communication device. So let me see if I got my pencil on here. So in the old days, the data terminal equipment would be your computer, and the data communication equipment would be that Hayes dial-up screeching cats modem. These days, the data terminal equipment is your home router. It's going to be your home router. And the data communication equipment is the DSL modem or cable modem. Now, these two devices may be combined into one box. The cable company and the phone company both are starting to do this. This is the customer premise equipment. That local loop, that last mile, that's the length of wire between you. That's the length wire that may be 100 years old and squirrels have chewed on it. I talked about the local loop and the last mile. The toll network is their connection, the telephone company or the cable company's connection to the internet itself. And backhaul networks and backbone networks are used to connect all those different companies together so you can get access to the entire internet. Voice band modems, dial-up modems like the old Hayes modems, not in much use anymore. These made the screeching cat's noise, and you would have to plug them into the back of your serial port of your computer. These have been mostly replaced by, since the mid-90s when broadband internet service became available, those have pretty much died out. We're probably going to use a cable modem or a DSL modem for residential use. In commercial environments, there was a device called a DSU-CSU, which would connect a digital device to a digital line. We used this back in the days when we moved all our IBM green screen terminals and all our printers to the gym, and you would come and register for class in the gym. We used a DSU-CSU to connect these back to our mainframe computer in Hearst at the Northeast campus, where you could get your schedule printed out. An optical converter is a device that converts between fiber optic cable and copper cable. The cable companies use this. They run fiber optic cables out to a neighborhood, and then they have a device called a node that converts the fiber optic pulses of light into electrical signals that go through that electrical coaxial cable that actually connects to your home cable set-top box. A wireless router access point, that's like a Wi-Fi access point that you can use to provide service to Wi-Fi devices. Now, the telephone companies themselves use very fast routers and switches. They're $1 million devices. They're not like our $500 switches and $1,000 branch office routers that we have in the Cisco lab. They're much more sophisticated than that. Now let's look at serial communication. Many years ago, probably before most of you guys have probably ever run into this, we would have parallel attached printers, and the printer would send 8 wires of data, all 8 bits at once, to the printer. The computer would send that data to the printer and would print it. And we would use a serial communication link for our dial-up Hayes modem. Where did all the printer ports go? No one has them anymore. Well, they use USB ports now, which are very high-speed serial ports. So it's all gone to 1 bit at a time. So all 8 bits go 1 bit down the time, 1 bit at a time down the wire. The problem with the old parallel system is if the wires got longer than about 10 or 15 feet, they could get out of sync with each other. So my very first job when I first came to Tarrant County Junior College back in 1981 was to hook a bunch of parallel printers, and each printer was shared among 3 or 4 computers in a student workstation lab. So I hooked these boxes up that would switch all 8 wires back and forth. If it went more than 15 or 20 feet, it got very unreliable. But serial connections can be made to go at a much higher rate of speed. So we're going to use serial USB. Ethernet is really a form of serial communication because 1 bit is set at a time. But we can do it at very high speeds, like gigabit or 10 gigabit Ethernet. Okay, concept now of circuit switch communication. When you pick up the phone and you dial somebody else, their phone rings, they pick up the handset and they start talking to you. And the telephone company switches establish a little, they snap together, a bunch of relays snap together a wire circuit between your phone and the phone of the person you're calling. And you can talk to them. Now, they don't have enough wires to connect everybody in the world at the same time. Try to call your mother on Mother's Day, and you probably may not get a connection because all the circuits are busy. When you hang up the phone, all those little relays and electronic points that connected your lines together open up, and the lines are now available for another phone call to be processed. So the phone company really only has about 5 or 10% of the wires as they have subscribers. And they're counting on the fact that most of the time your telephone is hung up. So that's a circuit switch. So when you use the old dial-up modems, you had a circuit switch connection to do that. Packet switch is like when you have an internet connection with a cable modem or a DSL modem, it's on all the time. You just shoot a packet into it whenever you feel like it. And all the devices that are connecting you to the internet, if they're not free right now, they're going to hold that packet in a buffer, memory buffer, and eventually it'll be switched back and forth. So examples of these is a Metropolitan Ethernet connection, DSL, and cable company service. Multi-protocol label switching is another technology that, don't worry about that. That's a CCNP topic. Frame relay has been taken out of the topology. We're not to worry about that. Asynchronous transfer mode was another technology that was the darling technology of the 90s. It was real good for voice and video and audio because it had little teeny weeny packets that we called cells. Now, talking about fiber optic connections, there's a couple of different ways that we can use to transmit our bits. This is typically not used by you. This is typically used by the service providers. They're going to use SDH or SONET to transmit data through these fiber optic cables and do the same thing that they originally did back in the 50s with copper cables. The telephone company came up with a technology in the 1950s to transmit 24 voice communications over 1 copper wire. It's called T1. And they took this same technology and they expanded to the fiber optic cables, which of course we could have hundreds of telephone calls at much higher rates of speeds over fiber optic cable because it's so much faster than twisted pair cable. Now, traditional WAN connectivity. In the old days, we would use a circuit switch dial-up modem, and our modem would dial the number. And we'd make the connection to that bulletin board system, or in the early days of the internet or StarText, we get a connection to America Online and get our early beginnings of the internet. Legacy. Anytime you see the word legacy, it substitute in your mind old, obsolete, should not be using it. Old, and we should use a more modern technology. So my old DSL connection that I got rid of a couple of years ago, that was legacy. No company not supporting it anymore. It made me switch to a newer technology. So in these days, we could, a point-to-point line, you could lease up from a service provider, a lease line like a T1 technology. T1 lines were about 1.54 megabit. They did have T3 lines that went to about 43 megabit. In the other countries, they're called E carriers. In Japan, they're called J1 lines instead of T1 lines or E1 lines. Very similar technology, just slightly different in the sense that Portuguese is slightly different from Spanish. So point-to-point communication is fairly simple. Just one point to another point. It's your private line, so you always get your full bandwidth you're paying for, and it's there all the time. The disadvantage is T1 private line is more expensive than a shared line, like the old frame relay services. And it's not flexible because you have to run a new line or add bandwidth if you need it. Okay, circuit switch connections used by the public service telephone network. This is like when you pick up a phone and dial somebody. The local loop connects your customer premise equipment, your telephone, to the central office. It's copper. Unless you've switched to the fiber. If you have the AT&T fiber connection, it's translated to fiber. But mostly it's always copper. So the public switch telephone network, public service telephone network, that's the traditional old legacy dial-up connections. And if you hook a Hayes modem to that, you can get about 56 kilobits. The phone company for many years has offered a service called ISDN, Integrated Service Digital Network, which we can get about 128 kilobits over that same old squirrel-chewed 100-year-old copper cable that goes back to the central office. And that for many years was a higher speed alternative to Hayes dial-up modem. But it's circuit switched. The old Hayes modems would take about 20 seconds to go through the screeching cat's noise and establish a connection. You would log into your server. ISDN can do it in 1 second. It's all digital, no analog to digital conversion. So packet switching is what we're going to use today, like a DSL modem or a cable modem. In the commercial world, we would use a frame relay connection where it was on all the time and you just shoot a packet into it, a frame relay frame instead of an Ethernet frame, and it would be connected to that other office. Asynchronous transfer mode is something that was very popular for audio and video because instead of a big Ethernet frame that was over 1,500 characters, ATM cells have a fixed length of 53 bytes, 48 bytes of data. So it was in the 90s, this audio streaming video started taking off, like for the marketing manager's video hookup they would have every week. So it was, but it turned out to be too expensive a technology. ATM devices were $800 or $900 for a NIC card to go into PC, and that just couldn't compete with Ethernet because Ethernet was less than $100. Now, modern WAN connectivity, we're going to use the internet and connect pretty much to everything else. Of course, we need an internet connection for our company to connect to the internet, so we can, get connections from our customers, and we can send email back to our customers and our trading partners and so forth. So the traditional T1 lines and dedicated lines have pretty much been replaced by internet connectivity. The problem is the internet is wild, wild west. Everybody can see everything. So if I want to send a secret marketing plan to the branch office, I can just encrypt it. And if you don't have the secret encryption key, you're not going to be able to see this. So we're going to use probably dedicated broadband connection. We can either go to a service provider and use the fiber they give us, or we can actually lease dark fiber and run our own network through it. In the world of packet switching, Metropolitan Ethernet is widely available, sometimes called carrier Ethernet. In big metropolitan areas like the Dallas-Fort Worth Metroplex, this is widely available everywhere. Now, if I want to go and connect a service station in Blum to my grandparents' house in Whitney, I probably won't be able to get a Metropolitan Ethernet connection because there's not much fiber in the ground down there in Central Texas. But in metropolitan areas, it's almost always available. So Metropolitan Ethernet and multi-protocol label service are good options for connecting to, even if one provider in one neighborhood is one company, another provider in another city is a different company. What if one's in France and one's in New York? Or we can just use internet-based connectivity because internet is pretty much available everywhere, usually broadband at high rates of speed. So let's use Ethernet wide area network service like Metropolitan Ethernet. I think Southwestern Bell calls this GigaMan technology. Ethernet over multi-protocol label service, or we can set up a virtual private circuit, which you're going to look at in the next chapter. So this is what we're doing with Tarrant County College. We have Metropolitan Ethernet service to all our campuses, and it's a very high rate of speed. It's like 10 gigabits. So the old rules, we had to put our Microsoft domain controllers, had to put a backup domain controller in each local office because it takes a long time to log in. Now we can put all our servers in a rack mount data center at Trinity River campus, and it's easy. They're in one place, they're easy to back up, they're easy to protect. And since the 10 gigabit connection to the other campus is so fast, everyone's going to be able to log in quickly. So they're very common choices these days for businesses and corporations. Multi-protocol label switching is a sort of a variant on the old frame relay protocol that we use. Every branch office is going to make a MPLS packet or frame and put a label on it. These are like the DELCIs, the data line connection identifiers in the old frame relay. And then as it goes into the provider circuit, he will look at that tag and send that frame to the right branch office where it'll be converted back into a standard old Ethernet frame. So these branch office routers, customer provided equipment, they just have to have an Ethernet port in them. You don't have to speak MPLS. Now, what are our options for connecting to the internet? We could use wired options. For example, we could use twisted copper cable. That's what I get from the phone company. They're wiring our neighborhood for fiber optics, and they're running commercials on TV for cheap optical fiber internet service now. Even the cable companies are doing this. So maybe I would be able to get a fast gigabit fiber optic connection in the future. Wireless options. What about if you live in an area like Blum, Texas, where there's no internet service connectivity? Well, I could use some sort of wireless thing. I could use Hughes satellite. Maybe some entrepreneur has put up a big tower in the farmland there, and he's going to offer wireless service from that. Now, wireless can be affected by weather. Just think of you guys have the, what is it called, dish service, where you get your TV channels through a rooftop antenna. Does it ever go out when it rains? Yeah, so you can get rain fade, and that can affect the data as well. DSL technology is what I had for many years, starting about 20 years ago. Always on. It uses the upper frequencies in a phone line that the voice doesn't use. The consumer version is called asymmetrical DSL because it's like 5 gigabits down and 1 gigabit up. That's perfect for browsing the internet because you want to download gobs of stuff, and the only thing you want to upload is the occasional D for download. Businesses, however, that have servers on their premises, they need symmetrical DSL, which is the same speed up and down, because they have a server on there and they need to serve up their web pages so customers will buy their products. DSL is dependent upon how long the line is to the central office, and it's generally not available if you're more than about 1 or 2 miles from the central office. So the DSL connection starts at the telephone company central office. They have a device called a digital service line aggregator module, and that's essentially a fancy Cisco router. And then that goes to the DSL modem that's at the customer's premises, and the DSL modem converts that proprietary telephone company format into standard Ethernet. Standard Ethernet connects to your home router, and you can connect to that. And the DSLAM module splits the voice communication and sends it to the voice dial-up network, and splits the internet data packets and sends them to the internet. DSL, traditional DSL use something called point-to-point protocol over Ethernet, in which it would take your Ethernet packets and encapsulate them in a point-to-point protocol frame, which is sent over serial ports, and that would go in the wire between your house and the telephone company's central office. It's also possible that that DSLAM would be located in a pedestal closer to you. So my telephone company's central office is in Kennedale. I'm in Southwest Arlington, and I'm too far from Kennedale to get a DSL, but there's a pedestal in the park a quarter of a mile from where I live, and the DSLAM aggregator is located there. Then they run fiber optic cable back to the telephone company's central office, and that was the telephone company called Project Pronto. So all these new neighborhoods that are being built in Southwest Arlington that were able to, they don't have to run a bunch of copper cable. They just run fiber to the neighborhood and then fiber to copper to all the phone lines. This is not used by the modern, very high-speed DSL service that I now get, which is about 75 megabit. So there's no extra overhead of the conversion between Ethernet to PPP and back. Cable technology uses a similar scheme in that at the telephone company's central office, at the telephone company head end, they have a cable modem termination system, which is another fancy $1 million Cisco router. Other companies make them too. and they run fiber optic cable out to that node in your neighborhood. The node up on a phone pole somewhere in your neighborhood converts the pulses of light in the optical fiber into electrical signals that can travel to the coaxial cable. They reach your home through that coaxial cable, go into your cable modem, and then your cable modem converts those into an Ethernet connection, that RJ45 connection, where you can plug your home router into the internet and get service. Okay, the newest technology, fiber to the home, fiber to the building, fiber to the neighborhood. And this is a bunch of marketing fluff from a lot of companies. They only seem to bring it to the rich neighborhoods like Richardson, and the people that live in the poorer neighborhoods don't get it, so I call it fiber to the press. They're crowing about this, but they're not living up to their commitments to bring this to all neighborhoods that should be able to get them. So fiber to the home is if I subscribe to AT&T's fiber service, they're going to run a piece of fiber right up to my back door, plug it into my hub that they give you. Now, do you think that the big super corporations, and let's see, what's the joke about the only social responsibility of a corporation is to increase the profits? I don't think they should have to compete with the municipalities, which can deliver internet service at a lower cost. If you're a municipality, you've already got conduits like sewers that you can run fiber through cheaper than a commercial business. They've got to actually buy and lay their own fiber. So municipal Wi-Fi, in some part, the corporations have been pretty successful at going on a state-by-state basis, divide and conquer, and go to the individual state legislatures and try to get municipal Wi-Fi outlawed or downplayed. As an example, when they had, what was it, Hurricane Katrina in New Orleans, volunteers put up a municipal Wi-Fi system so that people could, call their relatives that lived out of state and let them know they were okay. The Louisiana state legislature passed a law making them turn it off because the cable companies and phone companies in Louisiana did not want the free competition from the volunteers. Cellular is a very popular means of connecting. Most cell phone companies, you can turn it on, make it a Wi-Fi hotspot, and hook your laptop computer to it. If you live in an area where there is no cable service or no telephone service, maybe you can get a connection. You live in the middle of the Gobi Desert, maybe. There are still geostationary satellites that you can get service from. They're not that fast. They have latency, but you can still get service where you can't get it anywhere else through satellite internet service. Hughes, for example, is an example. Hughes internet service. Now, WiMAX, the giant corporations have taken over all internet service provider stuff. But there is one place left where the small business entrepreneur can still compete, and that's WiMAX. That is where you can put up your own tower and offer internet service in a small area that your tower can cover a few square miles. So if I go to vacation on the west end of Galveston Island, there's hardly anything out there but rattlesnakes and mosquitoes, and a few vacation homes that you can rent for a day. And the cable companies don't want to compete there. It's too expensive for them to run all those wires in there. So entrepreneurs have put up WiMAX towers, and you can lease them and use your Wi-Fi circuit that's in your laptop computer and get a connection to the internet and pay, $9 a day or something, and get connectivity when you're away from your home. VPN technology is, if we're going to use broadband internet service connectivity between the home office and the branch office, I don't have any control over security on the internet. Just assume that any packet you send to the internet, somebody else can spy on it. So you got to worry about Boris and Natasha seeing your packets and running Wireshark and seeing all your secret corporate data. But what I can do is encrypt my data before it leaves my facility, the secret key that only I know and only the branch office router knows, and use a public internet connection, which we need to have anyway because we want to communicate with our customers on the internet. And just use the internet instead of a private lease circuit that would be an additional cost. So it's going to save the company money. So far as security is concerned, I'll just use encryption. And if I need to add more scalability, add more bandwidth, well, I can just get a bit faster connection from my internet service provider. And it's compatible with any internet service technology that you can use today. So we would typically implement these using a site-to-site VPN that's configured on the routers, the client computers that are at those locations. They don't have to have any code on them. Or what if it's a salesman that's going to a sales convention somewhere? He could have a remote VPN software on his laptop computer and his Wi-Fi connection at the hotel, and it would encrypt the data, and then it would go back and he could connect to the branch office at home office and get that secret sales report that he's going to present at the sales meeting. Okay, so single home connection, just one connection, like at the top of the graphic. Dual home connection, in the residential world, I'm probably not going to do this. And so far as I'm concerned, that number 2 option is silly, because if AT&T goes down, both your connections to AT&T are going down. Let's look at the third option. If I'm a commercial customer, I'm going to have one connection to AT&T and one connection to Verizon. If AT&T goes down, Verizon is probably still up, vice versa. And that way I can use whichever one is available, or if they're both available, I'll just share the traffic over both of them. And then we're really getting on steroids here, have 2 connections to AT&T and 2 connections to Verizon. Any 2 unique service providers would work here. It just increases the expense of the circuits, at least on a recurring monthly expense. And let's see, this is the last one we're going to have for today. So if you work for a company and you're going to choose a solution, you're going to have to, what's the cost going to be? You're going to have to make a case that we need more bandwidth because everyone's productivity is slowing down. So the financial guy will buy you another circuit. So you could use cable or DSL for home users. Most businesses don't use cable or DSL. They use the commercial offerings from people like CenturyLink or AT&T commercial apps. If you do live in an area where fiber to the home is offered, that's usually 1 gigabit connectivity. And if you have a lot of streaming devices, so you want to download super fast, that's not that much more expensive than standard twisted pair connectivity. Cellular and mobile, cellular coverage is not available everywhere. You might be in an area where it's hard to get. Municipal Wi-Fi, if you live in a state where municipal Wi-Fi is operating well, I think Tennessee is an example of a state where municipal Wi-Fi is still allowed, and you can get cheaper service. But if you're in the middle of the desert, you can still use satellite communication and get connectivity that way at the highest expense and the slowest. Okay, I think I'm ready to finish this here. So what we're going to do is, you guys want to show up Thursday, we'll do the lab, and I'll do a lab run through of that on the real equipment in the lab. Okay, I'm going to say let's stop now, and I'll hang loose. First of all, I'll stop the recording.